Good day, everyone. I am Wilmer C. Hernando from BSME3A, and today we're going to solve problem 7.34 using the Mohr circle. So, without further ado, let's proceed to our problem. For the given state of stress, determine A. The orientation of the planes of maximum in-plane shearing stress, letter B. Maximum in-plane shearing stress, and letter C, the corresponding normal stress. So the first step is we need to draw a schematic figure of the stress element. Second step is we need to draw the Mohr circle representing all the stresses acting on the plane. As the direct stresses acting in x and y direction are tensile, their values are taken as positive, and the shear stress is acting clockwise direction on the plane, so its value is taken as negative. Obtain the coordinates of the point x by using this formula. Then we need to substitute 2 ksi for direct stress acting on x and negative 3 ksi for shear stress acting on x and y. So our point x is equal to 2 ksi and 3 ksi. So also, we need to do the same thing in point y. So, obtain the coordinates of the point y by using also this formula. So, we need to substitute 10 ksi for direct stress acting on y and negative 3 ksi for shear stress acting on x and y. So, our point y is equal to 10 ksi and negative 3 ksi. So, let's look in our Mohr circle. The point A indicates the maximum direct stress acting on the plane, and the point B indicates the minimum direct stress. The point D indicates the maximum shear stress acting on the plane. The normal stress acting on the plane is given by the abscissa of the point C. Calculate the normal stress acting on the plane by using the equation. So, we need to substitute 2 ksi for direct stress acting on x and 10 ksi for the direct stress acting on y. So, our average stress is equal to 6 ksi. Now, calculate the value of Fc by using the equation Fc is equal to OC minus OF. So, we need to substitute 6 ksi for OC and 2 ksi for OF. So, the value of our FC is equal to 4 ksi. Next is we need to calculate the angle of the principal plane by using the triangle XCF. Then, after, we need to substitute 3 ksi for Fx and 4 ksi for Fc. So, the angle of the principal plane is 18.43 degrees. Then, calculate the orientation of planes of maximum in-plane shearing stress using the following relation. Tangent to theta is equal to negative cotangent to theta. Then, substitute 18.43 degrees for theta p. Therefore, the orientation of planes of maximum in-plane shearing stress is equal to negative 26.57 degrees. As there are two principal planes which are perpendicular to each other, calculate the angle of the perpendicular principal by using this equation. So, 90 degrees minus 26.57 degrees is equal to 63.43 degrees. Therefore, the angle of the perpendicular principal planes is 63.43 degrees. The in-plane maximum shearing stress is equal to the radius of the Mohr circle. Calculate the maximum shearing stress of the in-plane by using this equation. So, we need to substitute 3 ksi for Fx and 4 ksi for Fc. So, therefore, the maximum shearing stress is 5 ksi. We need to calculate the maximum principal stress acting on the principal plane by using this equation. So, maximum stress is equal to OC plus AC. Then, we need to substitute 6 ksi for OC and 5 ksi for AC. So, our maximum stress is equal to 11 ksi. Then, we also need to calculate our minimum principal stress. acting on the principal plane by using also this equation. So, minimum stress is equal to OC minus BC. So, we need to substitute 6 KSI for OC and 5 KSI for BC. So, our minimum stress is equal to 1 KSI rather. To calculate the normal stress corresponding to the maximum shear stress, we need to use this formula. So the normal stress is equal to maximum stress plus minimum stress divided by 2. So we need to substitute 11 KSI for the maximum stress and 1 KSI for the minimum stress. So 11 plus 1 over 2 is equal to 6 KSI. So therefore, the normal stress corresponding to the maximum shear stress is 6 KSI. Thank you for watching.